Hello, welcome to the talk for correcting flaws in common disentanglement metrics. I'm Louis Mahan. In this talk, I'm going to first outline a difference in this that is articulated in the paper between what I call strong and weak disentanglement. Then I'll describe the two problems we identify with existing metrics and how we propose to avoid those problems. DCI, which is a particular metric, will get a short discussion of its own because it doesn't exactly fit into those two problems, but it has another problem. Then I'll describe the metrics we do propose, then introduce this task of a downstream task of compositional generalization, which is a useful way, we say, to evaluate metrics against each other. And then I'll present the experiments that show the correlation between various metrics and this downstream task, and how our metrics correlate the most strongly. Strong disentanglement and weak disentanglement. Well, there's a bit of a confusion in the literature, it seems, between two different things that disentanglement could mean. If you look at the original definition from Bengio 2009, it's just that each neuron represents a single factor, and it seems to allow that a factor can be represented by multiple neurons. As long you can have a set of neurons representing a factor as long as that set is distinct for each factor. The other definition, though, which is suggested by much of the treatment of disentanglement, and for example by this practice of latent traversals, where you change the value of one neuron and see what the output changes in response to that, and what you're looking for is that you change the value of one neuron and say one feature in the output changes. So this stronger version that's suggested is that there's a single unique neuron for every factor, and it's not really clear often which is being sought after and which is trying to be measured. The weak one, as you might guess, is easier to learn because the representation power of a set of neurons is much stronger and it can learn complex factors more easily. But the advantages to strong disentanglement are more obvious compared to, for example, an entangled representation. A strongly disentangled representation is more compact, and it's interpretable because you can see, you look at the value of a neuron and see what does this value indicate about the input or the output, which you can't do so much with a weakly disentangled representation, because you look at the value of one neuron and you don't know what part of the factor that it's representing does it actually represent. There's also a difficulty in trying to find the set of neurons that represent a given factor, because if you're looking for sets of neurons, there's exponentially many subsets of all neurons, whereas in the strongly disentangled case, you're just looking for an individual neuron. It's much easier to find the neuron that represents a factor. And we in this paper, so what we're saying is not necessarily that one is better than the other, but it should be clear, one should make clear which one they're going for, which of these two versions of disentanglement they're going for. And in our paper, we're looking at mostly strong disentanglement, though the downstream task is also relevant, as we'll see in the future, to weak disentanglement. Okay, what are the problems with the existing metrics in terms of now we're talking about strong disentanglement? Well, what most existing metrics do is they take the set of factors, and for each factor they find the most informative neuron. That can be the neuron with highest mutual information, with some strongest weight in a linear classifier or something like that. And they say that that is the factor that represents that neuron. And then they measure some version of, you want that factor to be very represented by that neuron and not be very well represented by any other neurons. But the problem is that they don't enforce that the neuron selected for factor 1 is different to the neuron that's selected for factor 2. And you can end up picking the same same neuron for different factors. And to show that this happens in practice, this is on the right a Hinton diagram, which is called a Hinton diagram for a beta TCV model that we trained on 3D shapes. And the size of the square in the ijth position is the mutual information between factor I and neuron J. And so what existing metrics basically do is take the largest square in each row and assign that to make that the assignment. So the largest square in each row is the neuron that is assigned to that factor in that row. So say in the very top row, the row that's measured 0, the largest square is in position 3, so they assign neuron 3 to factor 0. But if you look at neuron 2, that has very high mutual information with both factor 2 and factor 5. And so it ends up being assigned to both factor 2 and factor 5, which is certainly what you don't want. Even by weak disentanglement, you don't want that. You don't want that a single neuron represents multiple factors. So that's a problem. And the solution that we use here is that you don't assign each neuron individually, but you assign them all together in one big problem, and you enforce in that assignment that they're all unique. And that problem you're solving there is called the linear sum assignment problem. Then, and there's an efficient solution. It's solvable. Second problem concerns the distinction between independence and pairwise independence. So what most existing metrics do when they're looking to see if any other neurons represent the factor is that they just check those individual other neurons one at a time. And so this is we're in the setting where you've assigned a factor to one neuron, and now you want to check that none of the other neurons represent that factor either, because that's the desiderative disentangled representation. But they check each individual neuron one at a time of those other neurons, and that can miss cases when information is spread out amongst a whole set of neurons. It can be the case that for a whole set of neurons, each of them individually tells you absolutely nothing about the value of a particular factor. That is, they have zero mutual information. But together, they completely determine that factor. Together, they have maximal mutual information. The example on the right is it's actually the kind of negation of XOR, you might say. But XOR is a classic example of pairwise independence without independence. So we look at here in column 1, you've neuron 1 and the factor. Knowing the value of neuron 1 doesn't tell you anything about the factor. If you know that the value of neuron 1 is 0, the factor could be either a 0 or a 1. And if you know the value of neuron 1 is a 1, the factor could still be either a 0 or a 1. It doesn't narrow down your knowledge about what the factor is. The same with neuron 2. But if you know both neuron 1 and neuron 2, then the value of the factor is uniquely determined. So pairwise independence is not the same as independence, and you can't just check pairwise independence for each neuron with a factor. You have to check independence of the whole set of neurons with the factor. And what we do to measure that is we train an MLP to predict the factor from all the other neurons. And actually measuring mutual information in continuous values, especially with multiple inputs, is quite tricky. But training an MLP, we can roughly think of the accuracy of the MLP as a proxy for the mutual information. That if the information is there, we expect that the MLP will pick up on most of it and will get a high accuracy. If the information isn't there, obviously the MLP won't be able to get a high accuracy. So we train an MLP to predict the factor from all the other neurons, from all the neurons that aren't supposed to be encoding that factor. and we want the accuracy of that MLP to be low. DCI is a bit of a special case because it doesn't do this aligning neurons to factors thing. What it does is it computes a score for each neuron and factor, rather like the Hinton diagrams. And then it takes something like the entropy of each row and column, some kind of normalized version of that. So the previous problems don't apply to it, but something similar to the difference between independence and pairwise independence does apply. And that similar thing is that it can be that there are a set of neurons that represent a factor well, but none of them individually represent the factor well. So the representation is zero strong disentanglement in that there's no single neuron that represents the factor well. But in that case, the DCI score can get arbitrarily high. So basically, there can be a case, when we outline it at length in the paper, that there can be a case where DCI gives an arbitrarily high score even though the representation is zero strong disentanglement. And it's kind of due to the number of neurons. As the number of neurons increases, you can just observe empirically with DCI as well, that as the number of neurons increases, the score gets higher and higher. It also gets very slow to run, but the bigger problem is it gets higher and higher. And so there's a proof of this point in the paper. What are our proposed metrics? Well, we have two. We have one to measure how well the aligned neuron encodes its factor, and the other to represent how well, or measure how well, how much the other neurons do not encode that factor. The first metric, single neuron classification, aligns all the neurons to factors using this constraint that they have to be independent, they have to be unique. And then it says how accurately can you classify each factor from the neuron that's aligned to it. So if the representation is perfectly strongly disentangled, then for every factor there'll be a single neuron that perfectly represents that factor, and the accuracy of that single neuron will be 1 as a classifier. Using a neuron as a classifier, by the way, just means that you bin the values of the neuron and you assign the bins to different values of the factor. The details are in the paper, but it's quite straightforward. So that you can think of this single neuron classification as basically a quantification of what latent traversals show qualitatively. As you vary the value of a single neuron, how much does the corresponding factor vary? The second metric we call neuron knockout, because it measures the accuracy of predicting the factor after you've knocked out that one neuron that's supposed to be representing that factor. And actually, in order to get a more meaningful figure you can interpret as a score, we take the difference between an MLP trained on all the factors and neurons, and an MLP trained on all the neurons but that one aligned neuron. And so again, for a perfectly disentangled representation, the MLP trained on all neurons will be very high, but the MLP trained, when you remove just that one neuron, it'll go to zero accuracy, or go to chance accuracy, because all the information was in that one neuron and there's no information in any other neurons. This is a semi-formal definition at the bottom, where ACK of Z equals I means ACK of where only using neuron I, and then for NK, ACK full means with all neurons, and ACK Z not equals to I means the accuracy using all neurons but the ith. And there are two metrics. And then how do we evaluate these two metrics? We've given some theoretical arguments why they should be better, but it's a bit tricky to evaluate a metric, right? You have to, one way that you can do it though is you can come up with a downstream task that you know is important and that a good metric should be able to track, and then you can see how well the scores given by your metric correlate with the performance on that downstream task. And as a downstream task for disentanglement, we choose what is often called compositional generalization. It's mostly called that in the context of language, but we call it that here too. So humans, one indication that we do definitely disentangle concepts is that we can recognize a novel combination of concepts that we've never seen before, because we recognize each of the components individually. So when you see a purple giraffe like there is on the right, you've probably never seen a purple giraffe before, but you certainly know what the color purple is and you know what the shape of a giraffe is. So you have no problem saying that this is a purple giraffe. If you hadn't disentangled color and shape, you just have to say this is an entirely new thing that I've never seen before, I don't know what to call it. But humans have a very strong ability to disentangle. And the promise of disentanglement in artificial neural networks is that they will be able to do something like this too. That's part of the promise. So that's what we test as our downstream task. We take, for example, it varies depending on the actual data set, but for example, you train a model on a data set consisting of blue squares, blue circles, and yellow circles to classify color and shape. And then at test time, you give it a yellow square, and you see can it classify both the color and the shape. If it's disentangled them, it should be fine because the shape is familiar, the color is familiar if you consider them separately. But if it's learned some entangled version of color and shape where they're both on top of each other, then this yellow square is, you might say, out of distribution, and so it shouldn't be able to classify both correctly. That's the downstream task, and we measure how well each model can do that. A whole suite of models and a suite of datasets, and 3 datasets, and we also measure the scores for our metric and for existing metrics for all those models and those datasets. And then we take the correlation between the compositional generalization performance, that is the accuracy and these novel combinations of familiar features examples. We take the correlation between that accuracy and the scores of the metric. And it should be that the metric correlates very strongly with those scores, because if disentanglement really is the ability that allows you to correctly classify novel combinations of familiar features, and if the metric is measuring disentanglement, then it should essentially be measuring that ability. Firstly, you can see that there is significant strong to moderate or moderate to strong correlation for all of these metrics, which suggests that there definitely is some connection between disentanglement and compositional generalization. Incidentally, there's been some discussion in a few papers in the past about this connection between disentanglement and compositional generalization. Some have found that there is a connection, some claim there isn't a connection. The evidence we present here definitely that there is definitely that there is a connection, and we have a discussion in the paper of why we think previous papers might have missed the connection that is there. But definitely conceptually there's one, and then empirically we're showing there's one here too. The models, by the way, are beta V, beta TC-V, factor V, parted V. One calls itself weak DE, and another one's multi-type disentanglement. There are 2 more recent ones. All the details are in the paper. You can follow these names. And the data sets are D-sprites, 3D shapes, and MPI 3D. We showed the correlation for 3D shapes and across all data sets because in generally the scores for this compositional generalization task are pretty low. And for D-sprites and MPI 3D, they're actually so low they're at random guessing really. So you're not going to gain any insight from looking at correlation on such low figures, because it's basically just noise. But for 3D shapes, they're still kind of low, but they're certainly above random guessing. So there's a meaningful difference to detect here, and clearly the metrics are detecting it to some extent. And also, you can see the to the greatest extent, our metrics are detecting it, especially this single neuron classification metric. And so it's the highest correlation for both 3D shapes and on all data sets. And you can see in the paper calculations showing this difference is very significant with other metrics. So that's everything. Compositional generalization is a task that you can measure disentanglement metrics with, and based on results on those lines and in the theoretical arguments we've given, we're claiming that these metrics we're providing are a better way to measure strong disentanglement than anything that exists now. Thank you.